Hello, everybody. So today, I'll be discussing the secrecy framework we are developing at BU to enable data analytics in the cloud with provable security guarantees. This is joint work with my collaborators, Vasiliki, Kalavri, Faisal, and Mayank, Varia. So the secrecy framework targets a broad class of use cases where multiple data owners want to perform some computation on the union of their private data, but without revealing the actual data to each other or any other untrusted entity. Data owners can be healthcare providers, for example, hospitals that want to do a large-scale medical study on the union of their patient records, but they cannot simply exchange these records with each other due to strict privacy regulations. In another scenario, data owners can be financial institutions that want to do market analysis using their customer databases, but without revealing this data to competitors. Data owners can also be individuals, like, for example, web users who are willing to provide personal data to build better recommendation models, given that the recommendation service cannot track their online activity. Now, to realize all these use cases, we need novel data processing systems that can extract value out of private data, while also protecting data from unauthorized entities. We identify a common set of requirements for such systems. No matter what solution we come up with, it should protect data throughout the entire computation and should also allow data owners to outsource the analysis to untrusted third parties, for example, cloud providers. Another requirement is to support complex analytics. In many real use cases, computations are not about evaluating a single sum or a single average function. They can be complex data pipelines, like relational queries on one or more data tables. However, these queries are typically offline, meaning that they don't really require interactive response times, but still performance needs to be practical. And to put this in context, we should be able to do the analysis with no information leakage in a few hours. Supporting end-to-end secure analytics with practical performance is, of course, not a new problem. It is a long-standing challenge, and there are actually many approaches proposed by the systems and the crypto community. We can distinguish three main lines of work in this area. The first line of work includes approaches based on homomorphic encryption. Fully homomorphic encryption is a fantastic idea that enables computation directly on encrypted data, but unfortunately, it is still unpractically slow for the use cases we address. The second line of work includes approaches that use specialized secure hardware, like hardware enclaves. Enclaves are physically protected environments that were introduced by the systems community as a faster alternative to cryptography. This is a very interesting approach that relies on completely different trust assumptions. But the downside is that enclaves are prone to the so-called side channel attacks. Another promising approach is to use cryptographically secure multi-party computation, or MPC. MPC allows mutually distrusting entities to collectively compute the result of a function, for example, an aggregation, on data that no single entity can see. MPC provides information theoretic security guarantees, but it is still expensive. And the main reason it is expensive is because computing parties need to exchange a lot of data with each other during the computation. So the main challenge we address in our work is how to reduce the communication cost of MPC to make secure collaborative analytics practical. And to give you an idea of the cost I'm talking about, I collected some results from three recent works in the area. Existing papers report that MPC cannot scale well with the number of input records or the number of data owners. And in fact, some of these papers reported dramatic overhead, even when we have a handful of data owners and a few hundred input records. So these results have been around for a while now. And over the last few years, there has been a lot of cool research to address MPC overheads and scale secure computation to larger inputs. For relational MPC, however, existing approaches target peer-to-peer deployments and employ optimizations that require data owners to participate in the protocol execution using trusted resources. The secrecy framework that I will present today takes a fundamentally different approach and introduces cost-based optimizations that speed up MPC execution in the outsource setting. This way, it allows data owners and data analysts to benefit from the pay-as-you-go model of the cloud, since they can use untrusted cloud resources on demand. And at the same time, it allows cloud providers to offer MPC as a service. OK, let me give you an overview of the MPC setting we target with the secrecy framework. Data analysts can access a catalog of available private datasets, and they submit a relational query, a SQL query, to the secrecy service. Secrecy compiles the query into an optimal execution plan, provisions computing parties in available cloud providers. These cloud providers can be specified by the analysts when they submit the query. And then it instructs data owners to split their data into a bunch of random bit strings and distribute these random bit strings to the computing parties. This process, the process of splitting the input data into random bit strings, is known as secret sharing. And it is a very lightweight process that happens once in the beginning of the computation. The secrecy framework supports two types of secret sharing, arithmetic and Boolean. In arithmetic sharing, the secret that we want to protect is a number, an integer, that is split into 3 random numbers that add up to the original one. Whereas in Boolean secret sharing, the secret is a string that is split into 3 random strings of equal length, whose bit level representations XOR to the original one. So secret sharing is done locally by the data owners, and then each secrecy computing party receives 2 out of the 3 generated shares. So any 2 parties in this figure can reconstruct the original data if they collude, but any single party cannot, no matter how powerful it is. At the next step, the parties use the secret shares to compute the SQL query under MPC, according to a cryptographic protocol. And in the end, they open the results to the designated data analysts, who can reconstruct the true query output. Data analysts in the secrecy framework can also be the data owners themselves without affecting the security guarantees. And in fact, the system does not make any assumption about the actual physical deployment. It only requires that the 3 computing parties in this figure do not collude, which is the standard non-collusion assumption of MPC. The current version of the secrecy framework supports a typical semi-honest model, where computing parties do not deviate from the protocol execution, and protects against attackers who may have complete control over the network and can monitor all network links. And under this threat model, all data remain private as long as the attacker does not compromise the majority of cloud providers. This is an overview of the secrecy stack that we built entirely from scratch. At the lowest level, we have a library of primitive secure MPC operations. Operations like low-level operations like addition, like secure multiplication, logical AND, XOR. Then on top of this library, we have built a library of more complex operations that are based on these primitives. Operations like equality, inequality, secure compare and swap. And then on top of this library, we have built a library of secure SQL operators that can be composed to create arbitrary query plans. So the current version of the secrecy framework supports all common SQL operators, including selection, join, semi-join, group by with aggregation, sorting, distinct, and so on. All right, now let me give you a high-level overview of the core ideas in the secrecy framework. First of all, we carefully redesigned secure MPC primitives to work directly on database tables instead of individual records, so that we can amortize the high communication cost of MPC. Let's see how this works. In this example, we want to identify all records with a timestamp greater than a given threshold. And to do so, we need to evaluate one inequality per record. Using secret sharing, each inequality requires a logarithmic number of communication rounds with respect to the length of the timestamp in bits. So if we have n records in the data table and k bit timestamps, Applying the inequalities one by one requires n times log k communication rounds asymptotically. This is unpractically slow, especially for high latency environments, because each communication round in MPC is essentially a barrier. It is a synchronization point in the distributed protocol execution where the computing parties need to exchange some messages in order to make progress. The high number of network IOs actually exists in all secret sharing protocols. In general, they require communication rounds that depend on the size of the input. And exactly for this reason, secret sharing has been considered a poor fit for wide area deployments. To tackle this problem, the secrecy framework batches independent messages within and across inequalities and exchanges messages in bulk within the same communication round. This way, it evaluates the selection on the whole data table in log k plus 1 rounds in total, which is independent of the table size. This optimization is not specific to selections, and in fact, we have designed all secrecy operators to apply message batching by default. Otherwise, the cost of MPC is prohibitive. Message batching can result in up to 3 orders of magnitude better execution time, even when the computing parties communicate over high-speed Ethernet. When the computing parties communicate over the internet, the performance gains are even higher than those you see in the plot. The second core contribution in the secrecy framework is an analytical cost model that we defined to express the costs of query plans in terms of secure MPC operations. As you may know, traditional optimizations from plaintext databases rely on selectivity statistics to reduce the size of intermediate data during query evaluation. This approach works very well for plaintext data, but does not work under MPC. And to come up with effective optimizations in our setting, we need to express the query costs in terms of secure computation and communication primitives. So in the secrecy framework, we define 3 types of costs. The operation cost, that is given in number of primitive MPC operations required to evaluate the query. The synchronization cost, that is measured in number of communication rounds between computing parties. And we also define an extra cost of composing relational operators under MPC, that is again measured in number of operations and number of communication rounds. Let's see how we can use this cost model to generate optimal query plans under MPC. Consider a query that counts the number of patients per medication in a collection of medical records. A possible plan for this query joins the 2 input tables on a common attribute, in this case the patient ID, and then counts the number of records per medication in the join output. Evaluating this plan under MPC would require materializing and sorting the Cartesian product of the 2 input tables, which is expensive. To avoid this overhead, the secrecy framework generates alternative execution plans and uses the cost model to identify the plan with the minimum total cost. So in this particular example, it transforms the plan on the left into the equivalent plan on the right, which has a much lower cost under MPC. The total number of messages is reduced by a double logarithmic factor. The number of communication rounds is 4 times lower. And the space requirements are also reduced from quadratic to linear with respect to the cardinality of the input. In practice, this simple transformation results in 2 orders of magnitude lower execution time while retaining the full security guarantees of the cryptographic protocol. The third core contribution in secrecy is a carefully designed query engine for vectorized MPC execution that automatically applies a set of optimizations tailored to secure computation. And secrecy is actually the first system to take that approach. Until now, MPC systems for relational analytics offload the secure part of the computation to external general-purpose libraries, which are treated as black boxes by the query engine. For this reason, the optimizations they employ push part of the computation to data owners for plain text execution, or aim to reduce the secure computation to subsets of the computing parties, whenever this is possible. In contrast, the secrecy framework exposes the MPC costs to the query engine and optimizes the secure computation itself using a set of logical, physical, and protocol-specific optimizations that can reduce, can improve performance by orders of magnitude. Let's see some performance results. In these experiments, we use 8 queries in total, 5 queries that have been used in previous MPC works, and 3 queries from a popular database benchmark, the TPC-8 benchmark. In all experiments, we use randomly generated 64-bit secret shares, and we deploy each secrecy server in a different cloud provider. So the computing parties here communicate over the internet, and each server uses a single CPU thread for the secure computation. Logical and system optimizations result in up to 3 orders of magnitude better execution times, whereas other protocol-specific optimizations result in smaller but still considerable improvements. In some cases, we have up to 38 times lower end-to-end latency. This plot shows some results with increasing number of input records. All queries in these experiments include complex relational operators, like, for example, group by with aggregation, sorting under MPC, distinct, and can scale to 2 million input rows. The most expensive query is recurrent CDIF, a medical query shown on the right in SQL syntax, that completes in a bit more than 1 hour. Although the Secrecy project is pretty new, we already have a couple of real use cases. The first one is about secure analytics on mobile health data in collaboration with some faculty members from the BU Department of Medicine. Whereas the second use case is in collaboration with Red Hat and focuses on secure log analytics across multiple data centers. The goal of this project is to compute statistics on log generated by different OpenShift clients that will help Red Hat engineers identify common bugs and critical incidents and prioritize software updates. You can find more information about these use cases in the links. So the source code is available on GitHub. Please give it a try, give us feedback, and with that, I'm happy to take any questions.